closing keynote presentation is going to be given by Terence Barkan, who's the Executive Director of the Graphene Council. And I'd like to introduce him to you. He founded the Graphene Council in 2013 as a global trade and professional community connecting scientists, academics, producers, end users, and commercial professionals that all have an interest in the research, development, and application of graphene. The Graphene Council is a Tier 2 member of the Graphene Engineering and Innovation Centre at the University of Manchester, which is known as the home of graphene. Terence, can you hear us?
I can, Rob. How are you?
I'm all right. Thank you very much indeed. We can hear you too. It's wonderful to see you. Really good to see you. I know you've been very, very busy. I hope your meeting earlier today went very well. We can see you and we can hear you, and your PowerPoint is in the right format. So now it's time for you to give our very final presentation, our closing keynote final presentation. Thanks, Terence. Please take it away.
Thank you, Rob. Well, I really do appreciate this opportunity to speak to your audience about cement and CO2 reduction, and doing that through the use of an advanced material called graphene. I'm going to talk about how that works, how does graphene actually affect this kind of CO2 reduction, and then give some examples. For those of you, many of you may not have heard of graphene material. I'll explain a little bit about what that is. And there are many more reasons than just CO2 reduction to be excited about graphene when it comes to cement and concrete applications. Just for context, the Graphene Council is a trade association that represents this sector. We have a very large global community. I personally happen to be based in the US, but we have members from all over the world that work with this material. And this slide should give you an example of the range of companies. So as a nanomaterial, as an advanced material, graphene is quite applicable for the cement and concrete applications, but it works in many others as well. And this gives you an example of some of the other companies that are engaged with our organization. We've identified more than 45 different applications, and in fact, for graphene materials in cement and concrete happens to be one, and it happens to be one that's really garnering quite a lot of attention, including discussions we've had with the ACI, the American Concrete Institute, and with the Tennessee Concrete Association, for example, amongst others. Certain departments of transportation and people who are interested in the infrastructure sector in the United States have all expressed interest. And we have applications where graphene is actually being used in the concrete and cement field. So as everyone knows, obviously cement-based concrete is widely used, and everyone also knows that depending on which figures you refer to, it's accounting for approximately 8% of the global CO2 emissions, and it's a material that we depend on for many very good reasons, and we will continue to use it. And the question really is, how can we continue to use this material but reduce the CO2 footprint? According to the Portland Cement Association, and again, this is all information you all probably know at least as well as anyone, that when producing about a metric ton of cement, you're going to also create about 900 kilos of CO2. So that's really almost a 1-to-1 ratio of CO2 produced to cement. And then, excuse me, I want to share some information about an organization that's received a lot of visibility in this space, and that is CarbonCure, a Canadian company whose model is to sequester CO2 that's been obtained through other carbon capture venues. It could be from energy generation plants where the CO2 has been captured, and then it's transported to a cement production facility or a concrete production facility where it's then injected into the concrete so that it's sequestered there. And if we look at the figures that they've published, they have an impressive amount of about 110,000 metric tons of CO2 that have been sequestered in this way since 2011. And if we look on a, not a per capita, but on a pro rata basis, you're looking at about 4 kilos of CO2 that's sequestered per metric ton of concrete. And working backwards, that represents a reduction of about 4.3% of the CO2 that was produced in the cement for that same amount of concrete. And then this works it backwards to 1/3 of 1% of the global emissions. And while this is laudable, and we certainly are in favor of this approach, it still is not a significant reducer of carbon CO2. So if we look at concrete and graphene and what we can do in terms of CO2 reduction specifically, we look at it from this angle. Using an extremely small amount of graphene, which is a carbon nanomaterial, we've seen improvements in the compressive strength of concrete of 35%, the flexural strength of 25%, and importantly, I mentioned that there are benefits besides CO2 reduction. The cure time can be reduced by half or more through the addition of this material. We believe because it acts as a nucleating agent and it accelerates the crystallization process. But that's an important economic, economic and engineering factor when looking at adding this. And you can use as little as just 30 grams of graphene per metric ton of concrete. You know, this adds a small cost, but if you take into effect the higher cure rate, the potential to reduce the amount of cement content in it, if we could reduce that by 10%, for example, reducing the cement component by 10%, that equates to about 9 to 10 kilos of CO2 that would be reduced from a metric ton of concrete as opposed to 4 with the carbon cure method. And then, of course, these are not mutually exclusive processes. You could actually do both of those at the same time. So for those of you who don't know what graphene is, it is a two-dimensional, so a single atomic layer of carbon atoms that was discovered or isolated in 2004. The Nobel Prize in Physics was awarded for that discovery in 2010. And at this atomic level, the material behaves differently. You get quantum effects so that it behaves quite differently than the macro form of the material. So it's extremely thin, extremely strong, electrically conductive. It's a 20% flex modulus for a crystal, which is extremely high, very high thermal transport properties. And when it's used then in a host material, it can impart a lot of these attributes to the host material. Now, graphene comes in many different forms. So I mentioned it's a single atomic layer of carbon, but according to ISO definitions, up to 10 layers of carbon can be called graphene. So it's in graphene nanoplatelets. It can be obtained in the form of a powder, as a paste, or as a soluble solution. So graphene oxide is hydrophilic, so it actually can be put into water. And so you have graphene oxide with oxygen content, less oxygen, and a reduced graphene oxide, powder paste, or solvent, as I mentioned. And then also you can do functionalization, which many of our companies do, is they functionalize this material and they can tune it even specifically for cement and concrete applications so that it behaves in an intended way. So there's a lot of ways to use this material, and we simply suggest working with a knowledgeable graphene producing partner. And what do you get out of graphene? Well, as I mentioned, it's electrically conductive, thermally conductive, defends against UV degradation, extremely good at barrier properties. It adds mechanical improvement, and it's even a fire retardation agent. And then specifically, if we look at using it in cement and concrete, I mentioned the faster cure rate. You have an improved load strength, so that gives you some other flexibility, reduces water permeation. What's really important in adding the strength is also it's been seen to mitigate microcracking, so that then leads to further fractures. So it reduces that, and it can even be used not just in the original material, but also in repair compounds that are used. And by using less cement to get the same amount of performance, you can then reduce the amount of CO2 that's concomitant with that amount of cement. So that's an interesting way of doing it. And it doesn't require specialized equipment. It's like any other admixture that you're already using. You would simply use it into your compounding. And now who's actually doing this? So there's a number of companies that are producing graphene that is specifically being used in concrete and cement applications, including BioGraphene, Concrete Garmore, First Graphene Talga, and other companies that are affiliated with the Graphene Council. If you have an interest in this area at all, please contact us and we can put you in touch with the right people who have experience in doing these applications. And so just to give you some concrete data on how this works, one of the companies, Garmore, which is based in Florida, has a functionalized graphene oxide material, and they've had improvements of up to 45% in compressive strength, 25% in flexural strength, and a reduction in fracture or cracking. And they were able to take the cure rate and get the same or higher compressive and flexural strength in a 7-day cure as compared to a 28-day cure. So that's something important to think about. I mentioned the reduction of water permeability, and in this case, they're adding 200 grams of this graphene oxide material for a ton of dry cement. In graphene admixtures, we see another company called Talga, which has used this. In this case, they were getting a much improved cure time as well, but also flexural strength. So here you've got a 20% increase in flexural with only a 14% increase in compressive strength. And what I want to illustrate with these figures is that depending on the type of material and the mixture and the load factor, tune the material for the type of performance that's most important. So for example, if you don't really need more compressive strength because it's quite adequate, but you need more of the flex, then you can tune this material for that particular type of application. And then in another application, another example is where this concrete mixture was used because of its thermal properties, where offshore power generating cables, which generate quite a bit of heat, needed to be isolated and then to have the heat wicked away. And the thermal transport conductivity of the graphene enhanced material was 30% better than a leading market material that's used for that same purpose. So that's another way of looking at this. It really depends on your application area. The University of Exeter in the UK had an incredible 146% improvement in compressive strength and almost 80% in flexural strength, with only a 0.03% by weight addition of graphene in the final concrete composition. So again, just to give you some data, we have multiple data points, multiple research studies and applications using this material, getting some eye-popping results. Dr. Dimitar Dimov, who did his PhD specifically on the use of graphene in cement and concrete applications, is another expert in this field that shows really important, 34% improvement in compressive strength, 27% nearly in flexural strength. And in this particular case, they were testing using graphene with recycled cement and concrete products. A really important aspect for the industry is the increased use of recycled materials and trying to get their performance metrics up to virgin material type standards. And so that's another aspect for those of you who are looking at trying to use more recycled materials, but you're concerned about performance metrics, is graphene might be the right solution for those admixtures. Now, if we look at the economics of this, average price of dry cement in the US per metric ton is somewhere in the $95 to $125 range, using 200 grams of graphene per cement, which is less than what it would be in the final concrete mixture, obviously. And let's assume, for argument's sake, you could get a 30% price premium for a specialist high-performance product. That makes graphene competitive at $143 to $188 per kilo, when in fact, the market price for the graphene that can be used in this application is more like in the $50 per kilo range, all the way down to as low as $20 per kilo. Being used in these small amounts makes it very competitive then for these applications. And so if we look at that just with a little different vignette on that, if we look at what the price increases work out to on the lower right-hand side, the actual price in the final concrete mixture, depending on the increased cost, how much you're putting into the cement and how much is the price of the graphene, you're seeing somewhere in the range of 4, 5, or 6% actual cost increase to the final concrete product, which I know in a business that's as price sensitive as cement and concrete is significant. But you have to take into account the total aspect of the ability to reduce carbon, which has a value in itself, the increased cure rate, which has a financial benefit too on a work site. And so when you work through the economics, there are ways of recapturing these, what I would consider rather moderate price increases for a unique performing product. And so with that, I'm going to stop there, Rob. If anybody has any questions, I'm happy to take them. This is a very brief overview, but the main message here is graphene works in these applications. People are working with it today. There are companies basing their business models on using these superior performing cement and concrete mixtures. If anybody would like to learn more about it and how to get in touch with a graphene supplier that can help them develop these applications, all you have to do is contact us. We'd be very happy to put you in touch. We are a neutral trade association. We have no financial interest in any of the companies that we would recommend to you. That would be purely independent.
Thanks very much indeed, Terence, for a very interesting, thought-provoking presentation and a whirlwind tour, as you say, through the world of graphene. Very interesting. So perhaps unsurprisingly, we do already have a few questions that have come in. So Ricardo Rios says, does graphene have to be used during concrete batching? So could it also be mixed in with the concrete powder, for example, or does it have to be added during the concrete batching process?
That's a good question. So it could be added into the cement. The main issue would be just for dispersion. We'd want to make sure that it disperses well. So the conventional approach or the logical approach where it might be a little bit more effective is to put it into the concrete batching. But we do have companies that are looking at putting graphene directly into the cement mix in a dry phase. And another one is even looking at the aggregates and having that as the insertion point. But generally speaking, I think for ease of use, because you can use graphene in a dry form, in a kind of like a powder form, but it can also be, depending on the type of graphene, put into a liquid solution. And so if you're used to using admixtures in that way, then that would be a form that you could use. So the short answer is yes, but the concern would be with dispersion if it settles out. And just as long as it's evenly dispersed in the final mixture, that's what's important to get the right effect.
Right. Okay. Good. So Adrian Temple Brown has a question. How difficult is graphene to make?
That's a good question. On the one hand, it's not terribly difficult to make, but you're creating a material that gets down to the nanoscale where you're literally several atoms thick and maybe sub 1 micron to several microns across in flake size. And so there is certainly expertise required. A lot of graphene is made from graphite that's been exfoliated down to that several atomic layers of carbon level, and there are other methods of making graphene. Actually, almost any carbon source can be converted into graphene. So it just becomes a question of what type of graphene material you want to end up with. On the one hand, it's not terribly difficult, but there is expertise required to make sure you have a consistent batch of material that's actually down to that atomic level, and that's a little bit more of a specialist.
Now, I did hear that actually you can make graphene by taking a piece of sellotape, sticky tape, and actually wrapping it around a pencil lead and taking it off, and actually somewhere on that sellotape there will actually be some graphene.
That would be actually the way the Nobel Prize winners first isolated graphene was taking a piece of graphite and Scotch taped it and kept pulling it apart until it got down to 1 atomic layer. But nobody does that for commercial volumes.
Right. Okay. And so let me just point it out that they discovered this in 2004, and they got the Nobel Prize in 2010. 6 years between the discovery and the award of the Nobel Prize is unbelievably quick.
Yes.
Yeah.
Well, and even for a new material, for graphene today, and we just did an update for our members on the commercialization. We estimate that for the cement and concrete field that we will need somewhere between 110,000 to numbers north of that in metric tons per annum to serve this market. The current production volume is at 10,000 metric tons, but that's going to go much, much higher. The scaling for this industry is not the issue, right? There's plentiful graphite supplies. The production methodologies are known, and the capital equipment required to scale a graphene production facility, it's not like producing a semiconductor fab. It's it's $500,000 to a couple $1 million to make a production facility, as compared to hundreds of millions or something like that for some other sophisticated industries. So it's more about adoption. And we are, as the Graphene Council, we're actually working with ASTM to do a material specification for graphene. So we have an ASTM number, so you folks have an easier time of specifying the material.
Absolutely. It's going to be a question about getting this stuff in terms of the standards. I think that's going to be your rate limiting factor. So Adrian also says, how much energy is required to make 1 kilo of graphene?
That's a really good question. I don't have a direct answer for you, only because it is a very good, that's an issue that we're looking at. But for example, we have a large scale producer up in Canada that uses a mechanical exfoliation method. They have access to renewable energy source for electrical power, which is the primary input there. We also have another out of Rice University in Texas, a method called flash graphene, which uses an electrical charge, which actually on a per weight basis is not that much energy input to convert any kind of carbon bearing material into a graphene formatted material. So it really depends. There are electrochemical processes, physical exfoliation, high pressure water, liquid phase exfoliation. There's different methodologies and they each have a different energy profile. So I'm sorry not to give you a concise or numeric answer to that, but it's just there's a lot of variables in the type of material that's produced and the type of raw material that's used that has an impact on that energy input side. I understand the question. I'm just sorry I can't really answer it.
No, absolutely. Fair enough. So another question has come in, and it's again all about dispersion. So Emad Awais says, how can you mix 200 grams of nano-sized material into a ton of concrete, for example, and get uniform distribution of these very, very small quantities to get the high performance that you mentioned? So I think this is just a general kind of hurdle that you're going to have to get over for the cement and concrete industry. How do you get this almost perfect, infinite dispersion?
Well, it is an excellent question. So that's where the functionalization of the material comes in. So you can treat the graphene so that it disperses more evenly into the host matrix. And I would just compare it, this industry already uses accelerants or cure retardants or other nanomaterial admixtures that you're already using in these formulations. So from that perspective, it would be no different than what you're already using, which relies on a good dispersion within the host matrix. The trick is with graphene, with this material, is to have a partner that knows how to disperse. And we have companies that have the experience with putting graphene into cement and concrete applications. Also, with using the graphene oxides that are hydrophilic, helps to disperse because it can be put in the water phase that's added to your mix.
Absolutely. Well, Terence, that's all the time we have for questions. So I'm going to once again thank you very, very much indeed for being with us here today and for answering all of our very many questions. It's lovely to see you again, and hopefully we'll see you again another time very soon.
Well, absolutely my pleasure. Congrats on the event here in the U.S. and anybody who has an interest, please do reach out. We'd be happy to work with you or help you any way we can. Thanks, Rob. Thank you so much.
Thanks a lot, Terence. We'll see you again another time soon.
Take care.
Bye for now. Bye-bye.